Hello again and welcome to part 4 where we continue our discussions on waveguides. During this video we're going to talk about calibration. You can see off to my left I have some of the original standards that were supplied with the V2+4. I use these for the higher frequencies, and then I have a homemade set that I use for lower frequencies. These are good to about a gigahertz or so. I mentioned before that we can't perform the SOLT calibration with waveguides, and again that's because of how the waveguide behaves compared to a transmission line like coax. So again, if we just look at our Smith chart, if we plotted the short, it's going to be over here, the open will be on the right, and our load will be in the center. So with waveguides, we can create a short. This is a homemade one. This is nothing more than a copper plate, and then I've ground the end of this flat. And if this were bolted to the end of our waveguide, again, all the signal is going to reflect back, just like with the coax. So the shorted waveguide will also show up on the left here. You can see we have a load. This was produced by LRL, and again it's part of a university training kit. This is nothing more than a shorted out waveguide, and then it has a piece of absorbing material down the center of it. You can see it has a bit of a taper. I don't know if that'll show up in the camera or not. So again, the idea with this is that this is going to absorb all the signal just like a 50 ohm terminator would with a 50 ohm source. So with this attached to the waveguide, this will show up in the center as well. Now keep in mind, when we're dealing with coax, we're typically talking about a 50 ohm transmission line. So in this case, the terminator is indeed 50 ohms. The same thing that's normally supplied with these kits. The terminator is also 50 ohms. With waveguides, we're talking about wave impedances. And for WR90, which this happens to be, it's typically about 500 ohms, but that'll be frequency dependent. So while attaching the load, we will see a dot basically in the center of the Smith chart, just like we do with our 50 ohm standard, but again, it's not going to be 50 ohms. Now with a waveguide, when we attach an open, again, because it's not a reflective signal, well, you're not going to see that off to the right. It's actually going to show up close to the center of the Smith chart. So how do we actually produce this standard? It's fairly easy to answer. If you were to imagine taking your VNA, and let's go ahead and attach a short. So we get our dot off here to the left. Now let's move the short away from the reference plane. As we do that, what we're going to find is we're going to start to rotate around the Smith chart. And eventually, we'll end up over here. So this is going to be 1/4 of a wavelength. And you can think about it that we've calibrated to this reference plane, and with the short being a 1/4 wavelength away, the signal will have to propagate, hit the end of the tube, and then propagate back. So we're actually talking about a 1/2 a wavelength. So we're going to call this standard typically an offset short. This one's made by Murray Microwave, and you can see that's exactly what it looks like. This particular one is 14.48 millimeters. That works out to roughly 3/8 of a wavelength. So if we were to plot that on the Smith chart, again, this is a 1/4 or 2/8 of a wavelength. 3/8 of a wavelength is going to be located at the bottom of our Smith chart. Typically, you'll find that if a standard cal kit includes one of these, it also includes a 1/8 waveguide cal standard. And of course, 1/8 is going to show up at the top of the Smith chart like so. It would be a lot better for me to actually work with the 1/4 wavelength offset short. So what I've done is I've made my own. This is what it looks like. This part is made out of brass, and then I've copper plated it. So here's our 1/4 wave versus our 3/8 wave. While we could use this LR507 as our termination standard, unfortunately what I found with a lot of the parts that were included with those kits, the performance of them just isn't very good. Again, the purpose of those university study kits isn't to allow the student to make metrology grade measurements. It's really just to teach them the principles of how waveguides work. So really I'd like a better load standard than this. So this is the one that I'm using. This is made by Narda. It's a model number 300C. You can see this is a WR90 waveguide as well, and it's rated for an average power of 1 watt. Notice the VSWR on this is 1.015 max. You can see the taper on this is actually a cone. So basically it's spherical at the base, and it looks like it basically runs the entire length of this load standard. Again, comparing that with the LRL 507, which is basically a wedge stuck down the middle of it. So I don't expect the return loss for this to be near as good as what we're going to find with this NARDA part. I also have this load standard. Again, this is also made by NARDA. This is a model number 410-15. This has a VSWR of 1.353 to 1, or a reflection coefficient of 0.15. So at the bottom here we can see reflection coefficient. It's going to show up on this horizontal line here, and it's going to be out in this location over here. Now I had mentioned that this is a sliding load, and you can see this little plunger here moves in and out, and that's moving a set of fingers that are located down the center of this waveguide, and that's moving these back and forth down the length of the waveguide. As we change the length of that, it's actually going to plot a circle, and again, if we take like 5 data points or more around the arc, we can fit to a circle and then use that to calculate the actual center point. One question you may have is, how do they actually cause this mismatch error? Well, if we look at this waveguide, it looks like any other WR90 until we compare it against an actual one. So they mechanically set the mismatch by how the parts are machined. As long as we're talking about the mechanical design of this, another thing to point out is that this is made of 2 halves. And notice where the seam is. It's right down the center of the flange right here. It's not going this direction. In part 1 I was making my own waveguides, and I said that I was making those probably the worst possible way that you could ever do that. And one of the problems I mentioned is where I put the seams. Again, for me it was very easy just to take some brass and then bend it to form 2 L's and then solder the seams. So in my case, the seam is actually here and here, and again, that's not a good way to make a waveguide. Now for the through standard, it's going to be something like this little barrel here. And again, with our circuit board, it's going to look something like this. And again, the reference plane is going to be right down the center of this circuit board. For the waveguide, we'll attach 2 transitions together like so. That becomes our through. Again, we've calibrated to the reference plane right here. So bolting these 2 together is essentially the equivalent of our standard through here. During part 3 I compared several 3D printed horns. Most of these were printed out of PLA, and we looked at 3 different metrics. One of those, of course, was the radiation pattern that these produced. Another was the surface resistance, and the last one, of course, was the VSWR. And if you go back and watch that, you'll see we tried to measure the VSWR in multiple ways. One of those was using a slotted line. Now again, we used the one that was provided with the university training kit. This is the one that we had homemade. We also made the measurement by using the VNA with an external coupler. And of course, all the measurements that we made, we got different answers. And in the end of that video, I talk about the biggest discrepancy was due to this transition. So the idea of using these standards is now we are calibrating right to this reference plane. So we could remove some of the systematic errors that are caused by this transition. Now Dislord had provided me with firmware for the LiteVNA that allows me to use harmonics all the way up to 18 gigahertz. Now you may be asking, why not just take that VNA, connect it directly up to a transition like this, hook this up to the horn, and then just go ahead and measure the VSWR directly? Well, the problem is pretty simple. Basically, it's the same reason that I built the extender in the first place. The noise and the dynamic range of the Nano VNA just isn't good enough to make these measurements. This is the test setup that we're going to be using today. And off to my right, you can see I have our LiteVNA. One of the things I should mention is my buddy Flipper sent me this. This is a new version of the LiteVNA. If we plot the noise floor on the original one, there used to be 2 spurs that would show up at the lower frequencies. Those have been basically eliminated with this new hardware. The other thing that I noticed is that the noise floor on this new hardware is about 5 dB lower than what the original one was. And of course, if you follow my videos on the LiteVNA, you know that I ran into that problem where the voltage on the USB port would actually cause the VNA to create some internal noise. And the way we got around that is I put a series diode in line with the USB cable that drives these, and that really improved the noise floor on Flipper's original units. That problem seems to be addressed with this new hardware as well. For today, I'm going to be using the original hardware, just because that's what I started out with. Again, with this extender, what we're doing is we're taking the lower frequency range of the LiteVNA where it has a lower noise floor, and we're pushing that up to the higher frequency, in this case the X band. So you can think of it as essentially DC to 4 gigahertz, and we're converting that to 8 to 12 gigahertz essentially. So if we were to run these tests using the new hardware, I'd expect to actually see some improvements. So you can see I've permanently bolted our coupler to the extender just to keep things from moving around. If we want to make S21 measurements, all I have to do is detach our 2 pieces of coax and we're back to normal. So again, port 1 output, the signal propagates down the directional coupler to the device under test over here, and then the reflected signal comes out here through a small amplifier and then back into port 2. So again, to be clear, the software had to change, and that's because it's now using port 2 as the reflected signal. And that's not how the LiteVNA normally works. Again, the reflected signal is measured inside of this thing, not through port 2. So that's a change to my software and how it works. We'll go ahead and start our software and go to Setup Diagnostics, and we'll enable our extender. Now again, we're going to be using our directional coupler, so we'll select the external coupler, and again you can see our LO is set for 7.86 gigahertz, and that's defined by our DRO down here. And now let's change our frequency. We'll select the start frequency at 2 gigahertz and a stop frequency at 2.5 gigahertz. And let's go to reflection coefficient. You can see that we're now sweeping between 9.86 gig and 3.36 gig. And again, the way that that's working is we're taking the LO frequency, or the 7.86 gigahertz, and we're going to add that to the 2.0 gig. That's going to give us the 9.86 gig. So let's go ahead and we'll turn on the extender. And you can see we're reading about minus 30 dB down. The problem that I've got with this again is this directional coupler is only rated to 8.3 gigahertz. At 10 gigahertz we're running it much higher than what it was rated for. And of course this amplifier, I'm using this to gain back the loss of this coupler, and this amplifier is also only rated to 8 gigahertz. So we're running these parts way beyond what their rated frequencies are. If I wanted to improve this setup, I think the first thing I would do is just go ahead and replace the amplifier. But I think for these experiments, this setup will work just fine. So what we'll do next is run through a calibration. Normally to do that, what I'd be doing is attaching these standards, and I would be bolting these together, and I would torque all these down. Now for this experiment, I'm not even going to bolt these together, let alone torque them. I'm just literally going to lay these standards on top of our transition, and we'll run through the calibration that way. Again, I'll be careful to align it over the top of the port, but I'm just going to use gravity to hold these parts together. So let's see how this works out. So we'll run 2-port cal. We're going to do new, and we'll install the short, which is already there. Now for the open, we'll be using our offset short. Again, this will provide us our 180 degree phase shift. And now we're going to attach our load. Again, we'll be using this NARDA load. And for now, let's just save this to the default calibration file. So the first thing you'll notice, of course, we have the dot in the center. Let's go ahead and remove the load. And you'll notice that the dot moves down here in the lower quadrant. Let's go ahead and attach our short. And here's our dot off to the left. Let me just move the cursors over to that. And again, we'll take our offset short. And let's attach that, and of course the dot will move over to the right. So again, we got to make sure that this thing's fairly well squared up. Now let's have a look at the SWR. So you can see it's roughly 1.7 or so to 1. And again, let's take our NARDA terminator that we calibrated to, and again, this should basically provide a perfect VSWR. You can see it's roughly 1.01 at worst. Again, this part has a VSWR rating of 1.015 to 1. So of course, anything that we measure, we can't get any better than that. So when I ran all these tests the last time, I performed that at 10.16 gigahertz. So what we'll do is we'll reconfigure our VNA for CW mode. We'll set the center frequency to 2.3 gigahertz. And you can see that gives us a frequency of 10.16 gigahertz. And again, we'll select the x-axis to show us the samples. And of course, we have it set to 801 data points, or 0 to 800. So now the system is calibrated and configured to measure the SWR of the antennas the same way that we measured them before. When I measured these antennas the last time, this happened to be the best one out of the whole group. This gave us a VSWR of 1.08 to 1. And again, the radiation pattern for this was very similar to what the metal one was that this was modeled after. So what I'm going to do is just lay this on top of our transition. And again, we had measured 1.08, and now you can see with these standards we're measuring roughly 1.03 to 1. If we were to rotate the antenna, let's just clock at 90 degrees. So the polarization is way off. You can see we measure roughly 10 to 1. So let's go back to the Smith chart, and again, let's just take our horn and lay it up there. There should be a dot basically in the center. And sure enough, you can see right there it's reading a VSWR of 1.03 to 1. That's at 10.16 gigahertz. And again, keeping in mind that the impedance of the waveguide, it's not going to be 50 ohms. What you could do is set this to basically about 500. Normally what you do is select the normalized resistance to 1. So again, here's our 3/8 offset. And we said this should give us a dot basically at the bottom of the Smith chart. So let's go ahead and we'll hook this thing up. Again, we'll just be laying this on top of the transition. And look at that. It's just off by a smidge. Now, if you go to Murray Microwave and you look at this particular offset, what you'll find is they actually have an offset, and I think that the notes on that says it's something about their machining process. You'd have to go back and look, but I'm expecting this is going to be off by a little bit, but not by much. You can see it's basically at the bottom of the screen. Now we do have this other standard we can use for its sanity check as well. Now again, we'll just be laying this on top of our transition. And of course you notice that the dot is just off to the left of the center like we talked about. Right? If you look off to the left, you can see our VSWR is 1.36 to 1. Very close. And here we can see our reflection coefficient. Looks like it's drifting around a little bit, so 0.156, 0.153. Let's go ahead and plot the VSWR. You can see again, it's very close to 135 or so. It's a little bit higher. But again, this is without torquing anything. I'm just laying these parts together. So based on measuring these other standards, I can believe that the VSWR measurement for this particular horn is pretty close to what it actually is. I had mentioned that the terminators from LRL wouldn't make a good reference standard because their performance is so poor. Let's go ahead and hook one of these up. And you can see it's not quite a dot in the center. The VSWR for this is measuring 1.31 to 1. Let's just go ahead and we'll select standing wave ratio. We'll save this to memory 1. Now let's take our second terminator and measure it. And you can see it's quite a bit higher, so 1.37 or so to 1. So there's a discrepancy in the VSWR of 0.07 between these two transitions. Again, these are not meant to be a metrology grade standard. Earlier I had mentioned that I had collected some data with this VNA directly attached to this transition, measuring these same components. So let me just show you what that looks like. This is using the LiteVNA to directly measure the two loads from LRL. I collected the same data using my old Agilent PNA. See how much lower the noise is? Now I'm only running at 7.67 gigahertz here. This first plot is one of the LRL loads, and I'm directly measuring this with the LiteVNA. Now let's compare that what that same load looks like using the extender. You can see the red line way down here. Notice the difference in the noise between the two. Here's looking at our other load. Again, you can see the offset between the two. This is looking at our two NARDA loads. Again, the black line at the bottom having the VSWR of 1.015 versus the other NARDA standard at 1.353 to 1. Again, both of these very close. And let's plot that compared against how the LiteVNA measures that NARDA standard directly. You'll notice that the noise is much higher. The performance of this extender isn't very good, but of course I didn't spend a whole lot of money on it, but it does work well enough for these experiments. Well, I think that's going to be all for this video. What I might do in the future is take this new version of the LiteVNA 64, do some kind of a take apart video and compare the hardware against the original LiteVNA 64. Maybe we can see what's actually changed between the two. I really don't know. I haven't taken this thing apart since I received it, but I do know that the noise floor in this is quite a bit lower. And again, I had modified second LiteVNA where I changed out some of the caps and made a few other modifications to it, including the gain of the IF amplifier, and I did improve the noise floor for it a little bit, but not as good as what this one is. So it'd be interesting to see if this actually has a new circuit board layout or what actually has changed. I think that's going to be it for now. Hopefully you enjoyed the video, and we'll see you again soon. Later.